Damn it. Hi, Haley. How you doing, Haley? Okay, good. I think you're the, is that breakfast?
Yeah.
A good bagel. Man, I wish I had a good bagel right now.
It's actually a rice cake with peanut butter on it.
Oh, really? I thought it was a bagel. That must mean I'm really craving a bagel because everything I see is like a bagel. All right, so you're the only one that's dinged in so far. Tell me what you need help with, or you got a question about.
The optimization problems, the word
Okay.
problems, I still don't. They're just hard for me to do alone.
Well, they are hard, but let's just pick out one for me that you had a hard time with, and let's just ask some questions about them, okay?
All right.
Let's see here. Let me get some paper. Just if you got one in the book or you got one anywhere that we've already looked at, whatever, or anything on that page, that some of those on that sheet are tough, but we can look at them. They all work the same way, sort of.
What about number 3 on the guidelines for solving min and max problem sheet?
All right. Let me go back to that problem. Let me go back to that sheet and see what.
And it's the one under class problems. It's like the manufacturer wishes to.
Okay. All right. Let me go back and look at that one. Let me go back to my other stuff here. Max min problems. There we go. Optimization. And you said it was number, let me get back to this. Oh, I hadn't shared anything with you yet. Hang on. Let me share my screen since we're only looking at each other right now. All right. Okay. This is the one. Can you see the screen now? You okay?
Yeah.
All right. So the one you're looking at under class problems is this manufacturer wishes to minimize the cost of making containers.
Yeah.
Okay. All right. Let's look at that one. And I'm going to scroll down. I think you can sort of tell me what it says because I can't see both things at the same time. But let me get down here and find more paper here. All right. So what we got, if you read the problem, you're going to try to draw a picture, okay? And the picture in this case is of a box. So we're going to look at something that looks like that. So we've got a box, okay? Now, the main objective is to minimize what in this problem?
Cost.
Cost. All right, so let's just write that down first. Minimize cost. All right, so we don't know the size of this box. We only know one thing sort of about its dimensions. Read through the problem and is there anything there? I'm gonna let somebody in here. Is there anything there that tells you how to, anything about the box? Anything about the box?
It says that a container is to have a square base, a lid, and must have a volume of 36 cubic inches.
Okay. All right. So hang on, let's say, Katie, can you hear me?
I can. I'm so sorry. I'm late. It's
okay. We just got you and Haley here, so we're working on number 3 on the class problems on those optimization problems. Okay.
Oh, okay.
Okay. So Haley, you read all the right things, but what I'm going to tell you is that that I want you to read it a little bit at a time.
Okay, so
First thing.
the first thing is the volume of 36 cubic inches.
Okay. Actually, before that, there's something else that's said about the box, and I need that something else first. Did it say anything about the dimensions of the box itself? Not just the volume, but the dimensions of the box?
Like, if the top and bottom cost 12 cents per square inch.
Okay, I'm not quite there yet. Let me hone in on it. First of all, you got to have some variables here, okay? Guys that just came in, we're working on number 3 under class problems on the optimization problems, okay? So one of the first thing it says is it has to have a square base, okay? That's important here, because I need to label these sides. I know what I'm trying to do, but before I can minimize cost, I've got to have a good picture of what's going on with this. So I don't care what you label them. We could label this, I think I did in class, I just said, well, the base, if it's going to be a square, the length and the width are going to be the same. Okay? So the length and the width are going to be the same. You see where it says it has a square base?
Yeah.
Okay, so I got to have some variables here. Now, it doesn't tell me anything about the height. I don't know if it's a squatty little box or a real high box. I don't care. I just know that I'll just let that be Y. Okay, now let's start. After it said it had a square base, it said something about what the volume had to be. What did it say the volume had to be?
36 cubic inches.
Okay, so you know that's volume. It's in cubic inches. Volume is length times width times height. In this box, that's the length, that's the width, that's the height. I've got to have some variables before we start. So I know that whatever happens, this thing has to have a volume, in this case, x times y equal 36. So you see what I'm doing? I'm doing little things at a time. But if I can draw a picture, I really need to label it if it's not already labeled, okay? Because I've got to have some variables. Okay. Now, back to the main goal. Minimize cost. Here's something you can do that might help you to think this problem through. Put the problem in words. If you sort of break that box down, it's got a top. So I got to figure out the cost of the top. It's got a bottom. And how many sides does it have? I think we had a discussion about this in class, but how many sides? There's the top. There's the bottom kind of right in there. The top's right over it. How many sides does it have?
4.
It's got 4 sides, right? The top plus the bottom plus the 4 sides. Okay, that's not written very well. Okay, plus 4 sides. Okay, guys, Haley's asking me this problem, but if you need me to stop, just stop. What I'm doing, trying to do is to sort of teach yourself how to suck out the important parts of the problem. And if you can't write an equation for it, at least to begin with, write down in words what you're trying to do. Okay, so we want to minimize cost. We need the cost of the top and the cost of the bottom and the 4 sides. Okay, now what does it tell me about the cost of the top? Guys, what's it tell me about the cost of the top?
If the top and bottom cost 12 cents per square.
Okay, so stop right there. Per square inch, okay? Yeah. The top and the bottom cost, how much did you say? I forgot, 12 cents. 12 cents per square inch. So sort of back off of the problem and say, well, I need to know how many square inches are in the top and the bottom, because it's 12 cents for every one of those square inches. And when you see square inches, they're talking about area. If you see cubic inches, they're talking about volume. But if you see square inches, they're talking about area. So the question here is, if you look at the bottom and sort of bring it out like it is, it's just, the bottom just looks like that, x times x. I just kind of took it off the picture and put it down there. How many square inches are in this thing right here? Anybody? How many square inches? How many square, how many, what's the area of that thing?
2x.
Not 2x. You don't find area by adding, you find area by doing what?
X squared.
X squared. You find it by multiplying. Right? If this is a 2 by 3, it's got 6 square inches in it, okay? So that maybe that's part of the problem. So the top has X squared inches in it, X squared square inches in it, okay? And it's going to cost 12 cents for every one of those. So I got to figure out what the area of this is, because they're giving me the cost per square inch. All right, you just told me that the bottom was the same as the top. Otherwise, it's going to be a bad looking box. But the top looks the same as the box. The top looks just like that, and it also costs 12 cents. I'm talking backwards here, guys. I'm writing the top and the bottom, but they're both the same. Okay, they're both the same. Okay, so that's 12 cents times X squared for the top, 12 cents times X squared for the bottom. Now, let's look at the sides.
And the sides cost 9 cents per square inch.
Okay, so let me try this here. So the sides cost 9 cents per square inch. That's a cents mark per square inch. So once again, I've got to figure out how many square inches are in the side. If you look at every one of these sides, let's just concentrate on that side right there first. Concentrate on that side. What are its dimensions? What are the dimensions of that size? Anybody? That side. What's the dimension? What's the square inches in it?
X times Y?
Yeah, it's just X times Y. Look, square inches, if you're talking about a rectangle, it's always one dimension times one side times the other side. So that's X times Y square inches. Okay, so let's think about the sides again. The square inches in a side is X times Y. They cost 9 cents per square inch. And then how many sides are there, guys?
4.
4 sides. Okay, that's the cost of the sides. So 36 XY. Now, there's the cost of the top. There's the cost of the bottom. And there's the cost of the sides. And you've got your variables there, and your variables are in terms of your X and Y. You want to know what X and Y are, but you don't know them to begin with. So I know that the impulse is to just read the whole problem through, and you just keep reading it through every time, over and over and over again. You need to stop at little pieces and see if you can determine what those little pieces are. And what helps you sometimes is just to write it down in words. All right, let's see what happens after that. So we got the cost of this box is equal to, let's see, the top was 12x squared. The bottom was 12x squared. I'm going to put those two things together. So 24x squared is the cost of the top and the bottom together, because it costs the same. The top costs the same to build as the bottom did. Okay. The one thing that was different was the sides. And because there were 4 of them and they cost 9 cents each, we've got this 36 XY. Okay, 36 XY. Now, that if you think about it, that's sort of the heavy lifting in this problem. You have got the thing you want to minimize. You want to find out where that's minimum. Now, the only problem you've got is that it has more than one variable in it. You don't know how to differentiate something with more than one variable in it. You just know how to differentiate something with just all X's in it. And then this is where you're thinking, well, what haven't I used? What do I do? How do I find out what Y is in terms of X? Well, what haven't I used in this problem, guys? The problem originally told me that the volume of the box needed to be this. It needed to be 36 cubic inches. In other words, the volume needed to be x squared y equal 36. I have not used that. It did not have anything to do with the cost. So it's not something I wanted to use right away because the cost had to do with the dimension of the box. But what it is going to help me do is, whoa, sorry, I jumped here, sorry. What that is going to do is this. I know from that little piece of information that the volume has to be 36 equal x squared y. That gives me a link between x and y. And when you see little things like that that you maybe don't use in your equation, you're going to say, well, maybe there's some way I can use it later. Do you remember in the fence problems where we looked at, say, maximizing the area, but they told us something about the perimeter? And you wrote the formula for the area, but it was in terms of two different variables, like a length and a width. The perimeter is what helps you to find one in terms of the other. These are very similar problems.
Well, how did you get 36 equals x squared y?
Okay, go back, and I want you to tell me what the volume of that box is right there with the variables in it. What's the volume of that box? Length, width, height. Isn't that the volume of a box?
Yeah.
Length times width times height. In this case, I had labeled them x times y. So that's how I got right here. That's how I got x squared y. And they told me I needed to have 36 inches in it. So I call that a constraint. I'm saying, well, I'm going to minimize this box, but they're going to say, but you got to make it look, you got to make it have this many inches in it, or we can't use it. Okay. So I looked at my picture and I said x times y. So now what that does is give me the link between, I can solve for y in terms of x. And here's why that helps. Okay, did I answer your question, Haley? Do you see that's what the volume of the box I would have would be?
Yeah.
Okay, so what I've got here is I want to minimize C. It's 24x squared plus 36 times x times, now look at this thing right here. I need all x's in this thing, and I've got a y. But you know what? I've got a link between x and y here. If I solve for y, y would be 36 over x squared. Y would be 36 over squared. So you know what? That's exactly what I'm going to put in the place of y right there. And now it'll be in terms of one variable. Now, I haven't done any calculus yet. I'm just getting ready to do calculus. And I know that ultimately I'm going to take the derivative of this thing, and I have to have it in terms of one variable. Okay? I mean, some problems you don't have to do this. It's already in terms of one variable. But right here, that's what I have to do. So let's clean that up a little bit. X over x will be, leave me with an x in the denominator. So one of those x's goes out with one of those. 36 times 36. I finally have my calculator with me, which was buried in my car somewhere. 36 times 36 is 1296. Okay. Now let's talk about the calculus on these things. If you can get an equation that has only one variable in it, then what you can do is just take a look at the derivative of this thing. And is there anything I need to do to rewrite it to take the derivative, guys? Think about what I might need to do in order to take the derivative on this one. That's easy. What do I need to do to take the derivative of this thing?
Make x -1.
Yeah, make x to the -1. Remember all the rules we had on the last test about derivatives? So that's going to be 24x squared plus 1296 x to the -1. Okay, again, I haven't done any calculus yet, but now I'm ready. Because I've got the thing I want to minimize. I know when I want to minimize or maximize anything, I will take the derivative. So C prime here will be 48x minus 1296 x to the minus 2. Okay, so now I'm starting my calculus part of the problem. The hard part of the problem is setting it up. I mean, there's no question about that, but you've got to sort of use all your details, write everything in terms of one variable if you need to, and go from there. Now I need to find, what do we do to find maximums and minimums? For any of the stuff we've been doing, how do you find maximums and minimums?
So equal to 0.
Yeah, set it equal to 0. You're going to find the critical numbers. So this is going to look like 48x minus 1296. I don't want that. You got to rely on your algebra here, there, guys. I don't want that x squared in here. I mean, that x to the minus 2. So I'm just going to, bring it down now. All right, I'm relying on your algebra skills here. I need to solve that equation. Anybody got an idea about how I need to solve that equation?
So you need a common denominator of x squared.
All right, I'll find a common denominator. That's certainly one way to do it. That common denominator is x squared. This already has it. This needs another. X. Actually, it didn't have an x squared. It needs an x. It needs 2 more x's. So that's going to be 48x cubed. All right. Remember, I give the. See, this had a denominator of 1. So I needed to give it an x squared here. So if I give it an x squared there, I got to give it an x squared up there. So that's why I get the x cubed, guys. Okay, is everybody with me on the same algebra page here? All right, the only way a fraction can legally be 0 is if what?
The bottom is 0.
No, you don't want the bottom 0. That's how it's illegal, okay? As a matter of fact, if I let the bottom be 0, I would have a dimension for my box of 0.
Right,
so I really don't want that. The only way a fraction can legally be 0 is if the numerator is 0. All right, Katie, you okay with that? You understand why it's got to be the numerator?
No, I do. I thought you had asked us, because in previous times, we had always been like, if it's undefined. If
I know. I usually ask you the domain, and you're right. 0, I'd have to throw out 0, okay? So, but the idea here, guys, is if I want this whole fraction to be 0, I need to make the numerator 0.
Mm-hmm.
So I'm going to have 48x cubed minus 1296 equals 0. That'll give me the critical number. That'll give me what I want. All right, that's not a quadratic. I don't have a formula for it. Is there anything that can be factored out of it? I mean, what would you try at least? I mean, what would be nice if it really factored out? What could you factor out here?
You could try a 48, but
you could try a 48, and actually, that's about the only thing that's going to make this come out nice. If I pulled out a 48, and let's see what 48 into 1296 is. So I'm pulling a 48 out of it. It's 27. Wow, I couldn't have gotten luckier here because that's easy to solve. You know what's going to make that 0. You know a number cubed that's 27. What is the number cubed that's 27, guys?
3?
Yeah. Yep. If you don't see it, play around with it on your calculator. Now, let me say a word to you about factoring that 48 out. Honestly, we got kind of lucky here. If you didn't think to do that whole chunk at one time, you could pull a 2 out. Then you could probably pull another 2 out. Then maybe you could pull a 3 out. Keep pulling things out until you get to where you can't pull anything out again, okay? But I would, boy, if for my money, I would try to get that whole thing out at one time. If it doesn't come out, it doesn't come out. Just start again, okay? Now, what is that question?
Why did you drop the x squared again on the bottom? Because
okay, what's the only legal way? Look at a fraction. What's the only legal way that a over b can be 0? Can a denominator ever be 0?
No.
No. So the only way for that fraction to be 0 is if it were 0 over 2 or 0/3 or 0 or something. The only legal way for a fraction to be 0 is if the numerator is 0. Now, I'll tell you one other thing that might make this look a little better to you. There's another way to do this problem without finding the common denominator. You could multiply this whole equation here by x squared. That would give you the 4x cubed, and the x squared would cancel here, and that would give you that thing, and x squared times 0 would be 0. So it would really just give you that equation right there. I kind of like to do that instead of finding common denominators. I like to clear out the fractions. That's up to you.
How do you do that?
Okay, you see that denominator? I want to get rid of it. I'm going to multiply both sides by x squared. So that'd be 48x cubed. This x squared would cancel out. 0 times x squared is 0, and then I wouldn't have to worry about that anymore. I would just have that. But if you find, and your first instinct, Haley, was to find a common denominator, and that's okay. But in the end, the only way for, if you find a common denominator, the only way for the fraction to be legally 0 is if the numerator is 0. Division by 0 is anathema, undefined, terrible, bad, lousy. Don't have zeros in denominators, okay? All right, so what have we found? We found that one of the dimensions of this box has to be 3. So I'm gonna draw the box again and see what we did. There was the box. I had labeled that that base 3. We said it was a square. That's why I labeled it both with an X and an X there. So that tells me that this box, question?
Are we still doing the same problem?
This was the way this problem started, with a box.
Okay.
Okay. This was y. We got x equal 3 by x equal 3. Y, do I know how to find y? Do I know any connection between y and x? Well, yeah, I just used it a minute ago. It was 36 over x squared. And if x is 3, that would be 36 over 9. 9. And that's 4. That tells me that thing has to be 4. So this box is 3 inches by 3 inches by 4 inches. Now, does it satisfy the requirements? Well, yeah, it's gonna, that size box is going to give me the minimum cost, and it has a volume of 36 cubic inches. That's what I was looking for there. If I want to find its cost, those are the places where the dimensions of the box will give me the minimum cost. As with all the other problems I do, if I actually want to find the cost, I'll go back up to the cost function and plug in my x, and that'll tell me how much it costs. So I plug in.
Plug in 3.
Yep, exactly. I plug in.
And that'll tell you how much
the total cost of building the box is in cents. Everything's in cents because I didn't want to introduce any decimals into this thing.
But if you plug in 3, then what about the 4?
Oh, but 3. Well, you want to go back all the way back? The 4, but this x is sort of built. That 4 is sort of built in. You can go back to here if you want to.
Okay, so you could plug in 3 and 4.
Yeah, but see, the reason I had gotten down to this one that only had x's in it is because I knew I had to do that to differentiate it. But you can go back up here and plug them all in there if you want to.
Okay.
Okay. Okay. Now, guys, these problems, this probably is gonna be the biggest challenge on the test, perhaps, in terms of
yeah, they're so hard.
Yeah, things we've done. I mean, that's sort of standard. But use some techniques of just writing things down. Write down everything you know. Don't try to swallow the whole problem whole. You will choke if you do. Just do little pieces. Draw a picture if you can. Sometimes I'll give you a picture. Sometimes, as with the peach tree problem, you just need to set up a pattern. Okay. I think there was one in the book. I tell you what, there's one of those in the book. Let's look at one of those just to do one more of these things. Let me see if I can find it. It had to do with apples.
After this, could we go quickly over, I know we've done it a lot, but just one more time going over master lines?
Yes. Oh, absolutely. I can go to one of those, but I'm going to just set up a pattern on this other one, and then I'll let you guys finish the work on it. And then we'll look at a graphing problem where we have to do a master line. Okay. I may look at one on the review because it carries it all the way through pretty nicely. Where in the world is that stuff? It's in chapter 3. The one I'm looking at, I did a Peachtree problem in one of the lectures a couple of days ago. The Peachtree problem was in the apple tree problem was in, shoot guys, sorry. Let's get through here. Oh, here we go. 36. 36 on page 203. And then we'll look at all the way through it at a graphing problem. Okay, so 36, and here's what it says. If you've got your book, turn to your book, turn to page 203. It's number 36. It says a home gardener estimates that 16 apple trees will produce an average yield of 80 apples each. 16 trees, number of apples, 80 per tree. Okay? The problem here says that for each additional tree cuts down the yield by 4. Each additional tree cuts the yield by 4. So if I added 1 tree here, now if you do some thought processes like these, I'll give you some partial credit if you don't ever get to the end, but this is what you need to think about. How many apples will I have per tree if I add a tree?
So if you add 1 tree, you would minus 4 from the number of apples?
That's right. If I added 1 tree, for the 1 tree I added, I'd take away 4. That's what it means. Each additional tree cuts the yield by 4. If I added 2 trees, I would cut it by 2 4s. Now, you do need to kind of establish a pattern here. Don't go ahead and multiply it out and say it's 8, because I don't think you'll see the pattern if you do that. If I add 3 trees,
Say it's 8.
it's 8 for 2 trees, and then it'll be 4, it'll be 12. I'd have to take away 12, right? Because every additional tree cut it by 4. So if I added 2, it was 4 times 2 away. If I added 3, it was 3 times 4 away. Okay. So does everybody see the pattern here? And if you want to write that down, I mean, that's fine, but don't go ahead. I don't think you'll see the pattern unless you see what's happening per the 1 tree. So what I'm encouraging you to do is sort of leave these in there so you can see what's happening. Because in the end, what happens is this. All right, we sort of got the idea of the additional tree. Get rid of that. You don't know how many trees you're going to add. So suppose we add X trees. You got to have a variable. What will the yield be if I add X trees? Well, if I added 3, it was 4 times 3 that I had to take away. If I added 2, it was 4 times 2 that I had to take away. If I add X, what will I take away?
4 times X?
Yes. Because for every tree you add, you take away 4 times the number of trees. Now, yield is the total number of peaches. And the total number of peaches is the trees times the number of peaches per tree. So this is a times right here, guys. Times. So if I were to look at that, again, yield of, you got 80 peaches per tree, you got 16 trees. You want to know how many peaches? Number of trees times the number of peaches per tree. So if I multiply that out, I get Y is 16 times 80 which I think is 1280. Let me check that. 16 times 80. Yep, it's 1280. 16 times minus 4x is minus 64x plus 80x minus 4x squared. Here then I'll have minus 4x squared. Minus 64 plus 80, that's an 80 right there, is minus 16x. And then plus 1280. I just gathering things up, guys. Multiplying out. Now, there's an equation. There's an equation right there that you want to maximize. What do you do in order to maximize it? What do you do anytime you want to maximize something? What do you do?
What do you mean by maximize?
Maximize, find a maximize or find a minimum on a graph or anything else. You have,
Set equal to 0.
not until you take the
Derivative.
derivative, okay? You gotta
Sorry.
it's all right. I hadn't done any calculus yet, guys. So if you do one of these problems, you say, hey, wait a minute, I didn't do any calculus. You forgot something, okay? So there's y prime is minus 8x minus 16. And have I got, that's a plus 16x there. When I add minus 64 and 80, it's plus. Okay, so it's plus 16. Now I do what Katie said, because that's what's going to find me my critical numbers. I set it equal to 0. That, if you set it equal to 0, you'll get 8x equals 16 or x equal 2. Now, yeah, you got to think, well, what did the 2 stand for? The 2 stood for the number of additional trees.
Mm-hmm.
So if you started with 16, the number of additional trees that'll bump up your yield will be 2. You need to plant 18. Okay, so the answer here is he needs to plant 18 trees. Plant 2 more than he had, the 16, which equals 18. And then if you want to do the, if you want to find out what the yield is, it'll be 16 plus those 2. Actually, we already know that. 16 plus 2 will be this times this. Okay. All right, let me get back. Let me get to the part of the review here. Let me go and go through one that you have to do a master line for. Anything you want to graph, it's a good idea to have a master line because you got so much information. You got information about increasing, decreasing, concavity, local mins, local maxes. You need to try to do a master line. So there's test. Yeah, there's the. Let's see, that's it. Yeah, that's it right there. All right, let's do something here. Let me cut the light on, guys. I somehow got in the dark here. Okay. There are a couple of problems. Let's go over a couple of them. There's some you have to do all the work yourself, like this one. Okay. So what I ask you to do in this problem, I gave you a function, and I'm asking you to do all of these things. And then I'm asking you to draw a picture. So the first thing I'm going to ask you is the domain. With these polynomials with no x's in denominators, domain's minus infinity to infinity. Okay? If I want to find out increasing and decreasing, I take a derivative. And I find the critical numbers. So bring the 3 down here. I'd have x squared plus 2x minus 8. Factor it because that's the easiest way to find the critical numbers. The critical numbers here are 2 and minus 4. All right, can everybody see this? It's kind of dark on mine. That's better, I guess. So here's what you do. This first derivative line right here tells you about increasing and decreasing. That's what it tells you. You put those critical numbers on the number line and you test your derivative in each of those intervals. You know, you test it. I mean, maybe I didn't even give you a function. I'll show you one like that in a minute. Maybe I just gave you the fact that the derivative was positive in certain places. Well, anywhere the derivative is positive, you will have increasing. So when I test 3 in the derivative, usually easiest in the factored form, 3 minus 2 is positive. 3 plus 4 is positive. Positive times a positive is a positive. I put a positive over there. That means increasing. If I test something between 2 and minus 4, say 0. Remember now, I'm testing it in the derivative because I want to find out if the derivative is positive or negative. 0 minus 2 would be minus. 0 plus 4 would be plus. A minus times a plus is a minus. A negative first derivative means you are decreasing. Finally, if I test something to the left of minus 4, say minus 5. Minus 5 minus 2 is negative. Minus 5 plus 4 is negative. But a negative times a negative is a positive. You're putting it in the derivative. So that means increasing.
So I have a quick question. So when we are doing these and we're testing them, can we use any number that's above 0? Like we would just use like a negative number and a positive number?
No, you can use any number that's in the interval you're testing, Katie.
Okay.
So over here, if I'm testing this interval, I want to pick something this interval. I can pick 3, I can pick 10, I can pick 15. It doesn't matter. But when I plug it in, I've got to see how the whole derivative acts with it.
So you're using the critical numbers basically. And
I'm using the critical numbers to find out what intervals I need to test in.
Okay.
They split up the line that tell me what I need to look where it might change.
Okay.
That make sense?
Mm-hmm.
Okay. So one more example. I tested 0 here. I could have tested 1 because 1 is in between minus 2 and 4. If I test 1, 1 minus 2 is negative. 1 plus 4 is positive. A negative times a positive is a negative. So it's how the two of them interact, okay? You got to multiply them after you get them in there. All right, so then what I'll ask you to do is write it in interval notation. Well, that's easy. Where I had the positives was from 2 to infinity. Where I had the positives again was minus infinity to minus 4, so you can put a union on that.
Mm-hmm.
It was decreasing in between 2 and minus 4, which means I'll just put that in there. Decreasing from minus 4 to 2. Okay. The other thing you can tell from the derivative is local mins and local maxes. If you will put these arrows on the line, you'll see it. If it's increasing over here, your arrows, it's going up. If it's decreasing on the right side of minus 4, it's going down. That means I've got a high point right there. You see how it's coming up and then going down. That's a local max there. If you look at 2, you got decreasing or going down on the left, going up on the right. That's a local min. It's pointing to a low point. So you got a local max at minus 4. You got a local min at 2. You want to find out what they are? You always go back to the original because you're going back to the value of the function. Always go back to the original. So all I did here is plug in minus 4, and what I got was 27. When I plugged in 2, I got minus 9. That's what the first derivative tells you. That's the one line that has the information from the first derivative on it. Increasing, decreasing, local maxes, local mins. The next thing I do is always the same. I look at the second derivative. Well, here was the first derivative. The second derivative is 2x plus 2. So I took the second derivative. This is the line, this is the second derivative information. Find out where it's 0. It's just like a critical number, guys. We don't call it that, but it's the same thing. You find out where it can change, and things change signs around where there's 0. So when I pull out 2, I got minus 1 would make that 0. I put minus 1 on there. I will do the same thing I did with the first derivative, except this time I'm going to test it in the second derivative. If I look to the right of minus 1, say at 5, twice 5 plus 1, I'm going to the second derivative. Twice 5 plus 1 is positive. A positive second derivative means concave up. Positive second derivative means concave up, CU, positive. If I test something to the left of minus 1, say minus 3, I don't care what it is. I don't even care what it is when I plug it in. I just want to know if it's negative or positive. If I plug in minus 3 here, minus 3 plus 1 is minus 2. And 2 times minus 2 is negative. So it's negative there. I know it's concave down. So I do the same thing with the second derivative line, but it tells me about concavity up and down. I will write it in interval notation. It's concave up from -1 to infinity. It's concave down from -infinity to -1. A place where concavity changes, you know, when things change in the first derivative, it's local max and local min. When things change in the second derivative, it's called an inflection point. All right, so an inflection point, because it changed from down to up, my inflection point is at x equal -1. Now, it is a point, guys, and you do need to plug it in. If I plug in -1 to the original function, I end up getting 9. So the inflection point is -1, 9. Now, let me talk to you about here's what you want to see, Katie. You want to see a master line, and that's what I want to show you. And then we'll talk about how the graph comes from the master line. Are you okay with all that information? Forget about the endpoint stuff for right now.
Yeah.
Okay. So I'm going to go, and this is, I didn't have a lot of space here. You know what? Maybe I can add a page after this. Let's see if I can add a page after this. Let me add a page there. Aha, I got it. If it won't go away, add a page. Okay. Let's see. Okay, oh good, it added the page. Okay, so here's what I want to show you. I got my master lines all kind of squashed in down there. So I'm going to start a new master line here. What I'm going to put on the master line is all the concavity, all the increasing, and all of those numbers I've got. When I go back to look at these lines, both of them, the first one had a -4 and a 2 on it, and the second one had a -1. I'm going to put every one of those things on the master line in the right order. So -4, -1, and 2. So I'm going to put on -4, -1, and 2. Okay? Now, I'm going to look back at those individual lines. And I'm going to write down what's happening in those spaces. So if you looked at the increasing, decreasing, it was increasing to the right of 2, increasing to the left of -4. And in the middle, it was decreasing. So outside 2 and -4, it was increasing. So I'm going to write that. Outside 2 and -4, it was increasing, increasing. Everywhere between -4 and 2, that's before I even got to that -1, but it was decreasing. Okay, so I put all my first derivative information on there. Don't worry about the -1. It says it was decreasing everywhere between -4 and 2. So in every little slot you've got there, you put decreasing. Okay, you okay with that first part, Katie?
Mm-hmm.
Okay, let's go back to what the second derivative line told me. The second derivative line said everywhere to the right of -1, it was concave up. And to the left of -1, it was concave down.
Yeah.
Okay, this is where I ignore the other things on the line. To the right of -1, there's -1 right there. It was concave up. To the left of -1, it was
Down.
Concave down.
Mm-hmm.
Okay. Now, from those two pieces of information in from those lines, it will give you a shape.
Mm-hmm.
Increasing concave up, my pen's gonna go up and it's gonna hold water. So that shape right there looks like that.
But there are 4 shapes, right? Could you draw the 4 shapes just really quick?
Sure. Actually, I'm gonna draw them right here, okay? Because every one of them is represented here, okay? So increasing concave up means like that. Let's look at the other increasing. Increasing concave down means my pen's gonna go up, but it's not gonna hold water anymore. It's gonna dump water, concave down, okay? So there are the 2 possible increasing pieces. You can be increasing concave up and hold water, or you can be increasing concave down and dump water. All right, let's look at the decreasing ones. Decreasing means when I draw my pen, when I draw it with my pen. Now, as good Westerners, we go from left to right, okay? As I'm going from left to right, my pen is coming down. That's decreasing. Concave up means it's gonna hold water. So if I draw decreasing concave up, it's gotta look like that. Decreasing again, pen's going down, but concave down means it's gonna dump water. Okay? Now, let's see how that plays out with the rest of the graph, because you've pretty much got it now. If I start to draw the graph, I need to know the points that I had on it. And those come in the form of local maxes, local mins, and inflection points. I think my inflection point was at -1, 9. I'm not, I should write a scale on this, but anyway, that's the inflection point. If I go back, my local min was -427. I mean, my local max was -427. I'm sorry, that's local max. Local max was, I forgot what I said, -427. So over here, I'm gonna have -427. Make yourself a scale. I'm kind of doing this sloppy. My local min, so this is a local max. This was an inflection point. My local min, if I go back, was at 2 and -9. Now you should have all this stuff in front of you, okay? 2 and -9. Okay. 2. Oh well. Whoa, wait. 2 and -9. So here's 2, and down here is -9. That was a local min. Label the things, and it'll help you. Local mins are low points. Local maxes are high points. Now look at the shapes. I'm going to change color on the pen and put my shapes in. This first shape on the way to -4 has to be increasing concave down. So on the way to -4, right there, it looks like that. That's that. See that shape right there? In between -4 and -1, that's why I need to put these points on here. It's decreasing concave, oh, sorry. Get that out of there. It's decreasing concave down. It's this shape. Well, it's that shape. So it looks like that. Once I go between -1 and 2, it has this shape. So I literally just draw that shape. It's very subtle, but it's concave up and it's decreasing. Then it has this shape, means it's going to go up like that. So what your master line does, once you get your points on there, it tells you what shapes you need to get from point to point. Does that make sense?
Yeah, no, that was very, very helpful.
Okay, there's one other thing I could ask you. And the only other thing I could ask you would be absolute maxes and absolute mins.
Right. But
this doesn't have an absolute max now because it keeps going up. It doesn't have an absolute min because it keeps going down. If I give you endpoints, which I did here at -5, you need to plug those in and plot those points. So if I plug in 5, I get that. I got 27. If I plugged in -5, I got 23 1/3. Basically, you're cutting your graph off in between -5 and 5, and then you look to see what's the absolute highest y value.
Mm-hmm.
Well, what is the absolute highest y value once you found those endpoints and you compared it to everything else?
527.
Well, now, I said y value. So
27.
the absolute max is 27. It occurs at 5. What's
Okay.
your absolute minimum value?
-9
Where does it occur?
at 2.
Right. Okay, so that's the only other thing. I would suggest when you're doing this to get just your generic graph and then make a decent scale, because I didn't. But, go, where'd it go? Here. Make a decent scale put the -5 on plot it, and then put the 5 on plot it, and then you can say, well, that's all I really wanted to look at, the stuff between there and whatever 5 there, okay? And so it sort of cuts it off on either end, allowing you to see a highest point and a lowest point.
Perfect.
Okay. So that's what you're going to do every time. I mean, I'll give you varying forms of information. This is one where I just give you the function. You take the derivatives and everything. I might give you just the information, or I might give you the sign chart. But if you know it's a sign chart for f prime, you know it's going to tell you increasing and decreasing. If it's a sign chart for the second derivative, it's going to tell you about concavity. Then you put the information together, and you've got your master line. You can draw your picture. Okay?
Thank
Right.
you.
You're welcome. Anybody else? Any other questions? Okay, I will have the test posted by late this afternoon. I probably would suggest studying a little bit before you take it, maybe start it over the weekend. It is, it will be on Moodle. You'll see it clearly posted. Scan it to me like I usually do. I've got information on that on all the instructions on the front. And have it to me by Monday morning before class. And then I'll get that back to you.
You can post this video.
Say that? Yes, I will post it.
Okay.
I will post it, okay?
And this is open note or no?
Yes, yes. Open note, open books. The only thing I don't want you to do, I don't want you to talk to anybody else about it, and I don't want you to go online to try and find anything. Okay? That's the only 2 things I require. All the videos are fair game. You can look at those. You can watch me do a problem. Okay? Problems won't be the same, but the technique will be the same. You can use the videos. You can use anything I've posted on Moodle. Don't go on the internet. Don't talk to anybody else.
Okay.
Okay? I mean, you got me saying how to do it. I mean, that should help. Okay? All right. Questions, anybody? Anybody else? Okay, I will work on getting this posted after I get out of my 1 o'clock class, and I will maybe I can get it done now. I don't know, but it'll be on Moodle. I'll put it on Moodle as the class video for today.
Thanks for this extra session.
Oh, you're welcome. I will see you on Monday. Have a good weekend.
You too. Bye.
Bye.